Here we have Class 17, Kinematics of Rigid Bodies. This is an extension of Class 16, where we did rigid body acceleration. Now we're just going to do some more examples. This is the first example of 4. Take an example from Schaum's outlines again, and we have this linkage AB that is moving to the left at 24 inches per second, but it's also slowing down, right? So they're saying it has an acceleration of 40 inches per second squared to the right, which is another way of saying that it's slowing down. And we want to find the angular velocity and acceleration of CD. So I have this worked out, written out, so we'll go through it and I'll narrate. We start out with a velocity analysis of bar BC, and with using ICR, we're able to find, locate that ICR at the intersection of lines drawn perpendicular to those velocities at B and at C. And you'll note that the velocity of C has to either be up or down because of the arrangement of CD. Therefore, the line drawn through it goes here. We know the velocity of B, so we're able to figure out what the direction of the rotation is, and we discover that C is going upwards. So with the velocity of B equaling this omega times this distance right here, which we find to be 6, right? There's a 3, 4, 5 triangle with a long side of 10, therefore this side is 6. And we're able to divide that velocity of B by that 6 to be able to get the angular velocity about the instantaneous center of rotation. And then using that, we're also able to find the velocity at C, because we can multiply that angular velocity by this RC with respect to ICR, or 8 inches right there. Now we could do a velocity and a partial acceleration analysis of CD. We won't be able to find everything we want to know. We draw the diagram of that fixed link right here, fixed at D, and we're able to figure out the velocity of C. We already know the velocity of C, but we can use that to find the omega CD by dividing it by this length of the link, which we see up above is 6 inches. And we get 5.33 radians per second, and this one is clockwise. Notably, the one up above, this was counterclockwise. So that's partly the answer right there. We were asked to find the angular velocity of CD, and we sure did. So now let's try to find some acceleration stuff about it. Well, we're able to find what the normal acceleration is. That's going to be this, and that's in the x direction. So that's also going to be the acceleration of C in the x direction. So I'll change that on the next slide right there, but we could say that's the acceleration of C in the x direction is also the same thing as the acceleration of C with respect to D, the normal component of that. And that's just the angular acceleration squared times that distance RC with respect to D, or 6 inches, and we get 170.7 inches per second squared. There's not enough information yet to get the acceleration of C with respect to D in the tangential direction. So we can't quite get this one yet, but we're going to put that on the back burner and now investigate the acceleration analysis of BC. And we make our 3 diagrams, and we're focusing on point C, and we know the acceleration of B. It was given to us, so we use that as the translational reference right here in our middle diagram on this position that we care about. And then we take a look at the accelerations that are taking place at C with respect to B right here. We should take a look at the angles. In this solution here, I use the right triangle, or excuse me, the 3, 4, 5 triangle proportions. I don't usually do that. I usually find angles, but I think, I don't know what I was thinking when I wrote this up. So we write the equation for these three diagrams. The acceleration of c is equal to the acceleration of b, that's right here, plus the relative acceleration components, the tangential one and the normal one. In the x direction, we already know what this horizontal component is right there. We just got it from the previous analysis. So we march through this in the horizontal direction. We say this plus, now we have to break this guy down right here. We know that the tangential acceleration of this point C with respect to B is going to be that alpha BC right here, this alpha BC, and times the distance right here. And by the way, this was a guess, right? I guessed that it's going to be counterclockwise. I don't necessarily know that. I think we will find out that it is a good guess. I believe we find out it's a good guess. But if we were to turn out to end up getting a negative number, we would have said it was a bad guess. And so we only want but want to be careful, we only want the portion of it that is in the x direction. So for this vector right here, we will see that it's going to be that direction right there, right? That it's broken down into a y component and an x component. We only want the x component, so we take 3/5 of it. And then we also take a look at the normal component. That one's negative, but not because of any equation that we have on our equation sheets. We have to be careful. When we use the three diagram method, we're actually looking for what the signs are based on which way the arrows are going in our three diagrams. So we have negative because this x component right there is in the negative direction. And so that's omega squared, so that's omega BC squared times 10. So that's where the value is right there, and that 4/5 makes sure that we only are getting the horizontal component. But looking at this, we only have one unknown, so we're able to find what the omega BC is, not omega, but the alpha BC of this, and we get 43.12. With that, we're going to be able to go and find what the vertical, the y is now. So we go in the y direction and doing a similar thing. This is what I'm trying to solve for. And we know, by the way, that's going to get us that tangential one that we were missing on the previous page. So we march through the diagram here. In the y direction, there's nothing here in B. In the tangential part right here, the y component of it is going to be now 4/5. But now we do know the angular acceleration, so the tangential is of course going to be alpha times this length right here, this 10-inch length, and only the vertical portion of it. So that's why there's a 4/5 there. And then also we need to have the vertical component right here of the normal acceleration. So that's, once again, that's 4 squared times 10, and we take 3/5, and we're able to find what that vertical AC, the y part of the acceleration at C. Now we can go back to bar CD that we had on the previous page. All right, so we could take a look at this right here, and we're able to find, we just found the y component, which is the same thing as here. So we will come back, and looking through this, we're able to set those set this y component here that we just found equal to the angular acceleration of that CD times its distance. And we can then go backwards and find the angular acceleration. That's the thing that we were asked for to start with, is 73.8, and that's going to be a clockwise answer. So there you go. And hopefully the sound is better here. I bought a new microphone. It's made for podcasts, but let's see if that's improvement at all. Thank you. Almost 10 minutes.